Beneath the icy crust of Europa, a hidden ocean may exist, but new research suggests that any water attempting to rise through cracks could freeze solid within hours, turning the moon's potential into a frozen tomb. Scientists had hoped that this subsurface sea might offer a glimpse into life beyond Earth, but simulations reveal a chilling reality: the very process of water escaping could trap it in a labyrinth of ice, blocking any chance of sustaining life. This discovery complicates the search for habitable conditions, challenging the assumption that Europa's ocean is easily accessible. The journey from the depths of its ice to the surface is not just a matter of distance, but of time, so fast that the water might never make it. As we peer into the mysteries of Europa, we're reminded that even in the most promising worlds, the path to life may be blocked by the very forces that shape them. Europa, the icy moon of Jupiter, has long captivated scientists as one of the most promising places in the solar system to search for life. Beneath its frozen crust lies a vast, global ocean of liquid water, potentially deeper than all the oceans on Earth combined. For years, researchers have speculated that this hidden sea might harbor the ingredients necessary for life: water, chemical energy, and possibly even the building blocks of organic molecules. But a recent study has cast doubt on a key assumption about how this ocean might interact with the surface, complicating the search for habitable conditions. The new findings suggest that the journey of water from Europa's depths to its surface is far more challenging than previously thought, with turbulent motion, rapid heat loss, and the formation of ice crystals potentially blocking the path entirely. This discovery shifts the focus of the search for life on Europa, forcing scientists to reconsider how life might exist or how future missions might detect it. To understand why this is significant, we need to revisit the basic idea that has guided much of Europa research: the possibility that water from the moon's subsurface ocean might rise through cracks in the ice and form shallow reservoirs near the surface. These reservoirs, if they existed, could act as natural pools where chemical reactions might occur, or where life could potentially thrive. The theory is rooted in the way Earth's own oceans interact with its surface, how water moves through cracks, how it can mix with minerals, and how it might support ecosystems in extreme environments. If Europa's ocean could do something similar, it would open a new window into the search for extraterrestrial life. But the new simulations, published in a recent study, challenge this idea. Using advanced computer models, researchers have recreated the conditions inside Europa's ocean and the fractures that might connect it to the surface. The results suggest that the process of water rising through these cracks is not as straightforward as once believed. Instead of flowing steadily upward, the water would encounter intense turbulence as it moves through the narrow channels. This turbulence would cause the water to lose heat rapidly, a critical factor in maintaining liquid form. Europa's environment is extremely cold, with temperatures at the surface plummeting to -200 degrees Fahrenheit. If the water from the ocean loses too much heat too quickly, it would freeze before it could reach the surface, effectively sealing off the ocean from the outside world. The simulations also reveal that the movement of water through these fractures would generate ice crystals. These crystals, in turn, could accumulate and clog the cracks, further impeding the flow of liquid. The process is not just about heat loss, it's about the physical properties of water in an environment where temperature and pressure are vastly different from Earth. On Europa, the water would be under immense pressure from the ice above, which could influence how it behaves. The models suggest that even if some water managed to rise, it would likely form a thin layer of ice or a slushy mixture rather than a stable liquid reservoir. This would make it extremely difficult for any potential life forms to access the nutrients or energy sources they might need to survive. These findings are not just theoretical, they have real implications for the search for life on Europa. For years, scientists have proposed that future missions could look for signs of this surface interaction by studying the composition of Europa's ice or by searching for plumes of water vapor that might erupt from the surface. The idea was that if water from the ocean reached the surface, it would leave behind traces of its chemical makeup, which could be detected by instruments on spacecraft. However, if the process of water rising through the ice is so hindered by turbulence and ice formation, then these methods might not work as intended. The simulations suggest that any water that does reach the surface would do so in very limited quantities, and perhaps not at all. This means that the traditional search strategies for life on Europa might need to be re-evaluated. But this doesn't mean the search for life on Europa is over. Instead, it shifts the focus to alternative ways that life might exist on the moon. One possibility is that life could thrive entirely within the ocean, without ever needing to interact with the surface.
If the ocean is indeed a vast, stable environment with the potential for chemical reactions, it could support microbial life in ways similar to Earth's deep-sea hydrothermal vents.
These vents, which exist on Earth in extreme conditions, provide energy and nutrients for entire ecosystems, even in the absence of sunlight. If Europa's ocean has similar features such as hydrothermal activity or chemical gradients, it could be a self-sustaining habitat for life. This scenario would mean that the search for life on Europa would require looking deeper into the Moon's interior, rather than focusing on the surface.
Another angle to consider is the possibility that life on Europa might not rely on liquid water at all.
While water is essential for life as we know it, scientists are beginning to explore how life might exist in alternative forms or under different conditions.
For example, some researchers have speculated that if Europa's ocean contains dissolved salts or other compounds, it could create a briny environment that remains liquid even at lower temperatures.
This would allow for a more stable habitat, where life could potentially evolve in ways that are distinct from Earth's biology. The new simulations, which highlight the challenges of surface interaction, underscore the importance of understanding Europa's ocean in its full complexity, not just as a reservoir of water, but as a dynamic system with its own unique chemistry and physics. The implications of these findings also extend to the design of future missions to Europa.
NASA and other space agencies have long planned missions to study the Moon, including the Europa Clipper, which is set to explore the Moon's surface and its interaction with the ocean. However, the new research suggests that the mission's instruments may need to be adapted to account for the possibility that surface interactions are far less frequent or intense than previously thought. For example, if the water from the ocean doesn't reach the surface in significant quantities, then the search for chemical signatures or plumes might need to be more targeted. Alternatively, the focus could shift to studying the Moon's ice layer itself, looking for evidence of past or present interactions between the ocean and the surface. At the same time, the findings remind us that the search for life on Europa is not just about finding water, it's about understanding the conditions under which life might exist. The simulations highlight the complexity of Europa's environment, where the interplay of temperature, pressure, and chemistry creates a world that is both extreme and potentially habitable. This complexity means that any search for life must be guided by a deep understanding of the Moon's unique conditions, rather than assumptions based on Earth's experience. It also means that the search for life on Europa is part of a broader effort to explore the potential for life in the universe, where the rules of biology might be very different from what we know. In the end, the discovery that Europa's ocean may not easily interact with its surface does not diminish the Moon's potential as a habitat for life. Instead, it challenges scientists to think more creatively about how life might exist in such an environment. Whether life on Europa thrives in the ocean itself, in alternative forms, or in ways we have yet to imagine, the search continues. The new simulations are not a setback, they are a step forward in understanding the Moon's mysteries. As we look to the future, the search for life on Europa will require patience, ingenuity, and a willingness to adapt our assumptions. After all, the universe is full of surprises, and sometimes the most important discoveries come from rethinking what we thought we knew. For decades, Europa has captivated scientists with the tantalizing possibility of life beneath its frozen crust. This moon of Jupiter, with its icy shell and a vast subsurface ocean, has long been considered one of the most promising places in the solar system to search for habitable conditions. But the path to understanding this hidden world has never been straightforward. The journey to confirm the existence of these oceans and to determine whether they might be accessible has involved decades of observation, technological innovation, and a growing understanding of the complex physics at play. Now, a new study is cast doubt on a long-held assumption that water from Europa's ocean might rise through cracks in the ice to form shallow reservoirs, making it easier for future missions to study. How did scientists arrive at this conclusion? What tools and methods have they used to unravel the mysteries of Europa? And why does this finding complicate the search for life on this distant moon? Let's walk through the science behind this discovery. The story begins with the first hints that Europa might harbor an ocean. In the 1970s, NASA's Voyager missions captured images of Europa's surface, revealing a world of chaos, cracks, ridges, and a surface that seemed to shift and stretch. But it wasn't until the Galileo spacecraft arrived in the 1990s that scientists began to piece together the puzzle.
Galileo's instruments detected a magnetic field around Europa, a sign that something conductive, like liquid water, might be lurking beneath the ice. The data suggested a global ocean, possibly tens of kilometers deep, sandwiched between the Moon's icy shell and its rocky interior. This discovery transformed Europa from a cold, lifeless rock into a potential cradle for life. But how do you confirm the existence of an ocean beneath an ice shell? The answer lies in the interplay between gravity, magnetism, and the Moon's internal structure. Galileo's measurements of Europa's magnetic field, combined with Jupiter's intense gravitational pull, provided indirect evidence of a subsurface ocean. The Moon's surface, however, remained a mystery. Scientists speculated that the ice might be several kilometers thick, with the ocean below remaining isolated from the surface. Yet, the idea that life could exist in such a hidden environment sparked a new question: if the ocean is sealed away, how could we ever study it? The answer, many believed, might lie in the Moon's dynamic surface. In the early 2010s, a breakthrough came when researchers proposed that Europa's ice shell might not be a static barrier but a dynamic, shifting layer. Models suggested that tides from Jupiter's gravity could flex the ice, creating fractures and allowing water to rise through the crust. This idea led to the hypothesis that the ocean might vent through these cracks, forming shallow reservoirs of liquid water near the surface. If true, these reservoirs could act as a bridge between the deep ocean and the surface, allowing future missions to sample the water without drilling through kilometers of ice. The concept was revolutionary. It meant that Europa's ocean might not be entirely inaccessible, but rather a world of hidden hydrothermal vents and chemical interactions, waiting to be explored. But how did scientists test this hypothesis? The answer lies in a combination of observational data and computational modeling. Researchers used data from Galileo and later missions to simulate how Europa's ice might behave under the Moon's extreme conditions. They considered factors like the Moon's orbital resonance with Jupiter, the tidal forces that flex the ice shell, and the thermal gradients that might drive water movement. These models suggested that the ice shell could be fractured in ways that allow water to migrate upward. However, the key question remained: could this water actually reach the surface, or would it freeze before it could escape? This is where the new study comes into play. Published in 2026, the research built on earlier models but introduced a critical twist: the dynamics of water movement through fractures. The team, led by planetary scientists at NASA's Jet Propulsion Laboratory, ran simulations to track how water from the ocean might travel through cracks in the ice. They considered the physical properties of water under extreme conditions: its viscosity, thermal conductivity, and interactions with the surrounding ice. The results were sobering. The simulations revealed that as water rose through the fractures, it would rapidly lose heat to the frigid environment. This cooling would cause the water to form ice crystals, which could clog the fractures and prevent further flow. In some cases, the process might take just hours, effectively sealing off the ocean from the surface. The implications of this finding are profound. It challenges the assumption that Europa's ocean is easily accessible and forces scientists to reconsider how life might exist in such an environment. If the ocean is largely isolated, then any potential life would have to adapt to extreme conditions, perhaps thriving in hydrothermal vents deep within the ice, or relying on chemical energy rather than sunlight. The study also highlights the complexity of Europa's ice shell, which may not be a simple barrier but a dynamic, layered structure with its own internal processes. This complexity means that future missions must be designed with a deeper understanding of the Moon's geology and physics. But how did scientists arrive at these conclusions? The answer lies in the collaboration between planetary scientists, oceanographers, and computational modelers. The team used high-resolution simulations to model the behavior of water under Europa's unique conditions. These simulations accounted for variables like the Moon's temperature, pressure, and the mechanical properties of ice. By running thousands of scenarios, they could determine the likelihood of water reaching the surface. The study also drew on data from previous missions, including the Galileo spacecraft and the Hubble Space Telescope, which had observed plumes of water vapor erupting from Europa's surface. These plumes, if they are indeed vents from the ocean, suggest that some water does reach the surface, but the new findings indicate that such events might be rare and localized. This brings us to the broader implications for the search for life on Europa. If the ocean is not easily accessible, then the methods used to detect life must evolve. Instead of looking for surface reservoirs, scientists might focus on other indicators such as the chemical composition of the ice shell, the presence of certain isotopes, or the detection of organic molecules. The upcoming Europa Clipper mission, set to arrive in the 2030s, will play a crucial role in this effort. Equipped with advanced instruments, the Clipper will study Europa's surface and subsurface in unprecedented detail, searching for signs of activity that could hint at the presence of an ocean. It will also test the feasibility of future missions that could drill through the ice or land on the surface to collect samples. The journey to understand Europa has been a testament to the power of scientific inquiry. From the first hints of an ocean to the development of computational models that reveal the moon's hidden complexities, each step has required ingenuity and persistence. The new findings, while sobering, underscore the importance of continued exploration. They remind us that the search for life in the solar system is not about finding easy answers but about embracing the unknown and pushing the boundaries of what we think is possible. As we look to the future, Europa remains a beacon of possibility, a world where the line between science fiction and reality continues to blur, and where the quest for knowledge drives us ever forward. Europa's hidden ocean has made the icy moon one of the solar system's most promising places to search for habitable conditions. Scientists have hoped that water from this deep ocean might rise through cracks and form shallow reservoirs that future spacecraft could more easily study. New simulations suggest that journey is unlikely because turbulent water would rapidly lose heat, form ice crystals, and clog the fractures, sometimes within hours. This part of our deep dive into the search for life on Jupiter's icy moon Europa just got more complicated. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, Europa has been a tantalizing mystery in our search for life beyond Earth. Its icy surface, crisscrossed by chaotic cracks and ridges, first caught our attention in the 1970s when NASA's Voyager 1 and Voyager 2 flew by the Jovian system. These spacecraft revealed a world unlike any other, a small, frozen moon orbiting Jupiter, its surface glowing with a pale blue hue. But what truly set Europa apart was the faint, subtle patterns on its ice, which scientists began to interpret as evidence of a hidden ocean beneath. The idea that liquid water might exist beneath an icy shell was revolutionary, but at the time, it was more speculation than confirmed fact. The Voyager missions had shown Jupiter's intense radiation belts and the moon's extreme cold, yet the possibility of a subsurface ocean lingered as a tantalizing hypothesis. It wasn't until the 1990s, with the arrival of NASA's Galileo spacecraft, that this hypothesis began to take shape. Galileo's instruments, designed to study Jupiter and its moons, provided the first direct clues. The spacecraft's imaging systems captured Europa's surface in stunning detail, revealing a landscape of ridges, roofs, and chaotic terrain that suggested something was actively shaping the ice. Most compelling was the observation of what appeared to be chaos terrains, regions where the surface seemed to have been disrupted, with blocks of ice jumbled together. These features, scientists argued, could be the result of tectonic activity driven by the moon's internal heat, possibly indicating that liquid water was rising and interacting with the ice above. Galileo's data also hinted at the presence of a subsurface ocean, though the evidence was indirect. The spacecraft's magnetometer detected a magnetic field that suggested a conductive layer beneath the ice, which could be a saltwater ocean. This was a major breakthrough, but it was still a puzzle. How could such a vast ocean exist in a moon so far from the Sun? The answer, scientists speculated, lay in tidal heating. Europa's orbit around Jupiter is elliptical, meaning the Moon experiences intense gravitational tugs from the gas giant. These forces flex the Moon's interior, generating friction and heat. This process, they argued, could maintain a global ocean of liquid water beneath the ice, potentially hundreds of kilometers deep. The discovery of this ocean transformed Europa from a distant, icy world into a prime candidate for extraterrestrial life. But the question remained, how could we study this hidden world? The answer, for many years, seemed to lie in the idea of shallow reservoirs. If water from the subsurface ocean could somehow rise through cracks in the ice, it might form temporary pools or lakes on the surface. These features, scientists believed, could be accessible to future missions, offering a way to sample Europa's ocean without drilling through kilometers of ice. This concept gained traction in the early 2000s, as researchers began to model how such a process might work. The idea was that tidal forces might not only keep the ocean liquid but also create pathways for water to escape. If these pathways existed, they could allow for the exchange of materials between the ocean and the surface, potentially creating environments where life could thrive. The hope was that future spacecraft could land on Europa, drill into these shallow reservoirs, or even detect signs of biological activity through spectroscopy or other remote sensing techniques. This vision of accessible water on Europa's surface became a central goal for planetary scientists, inspiring missions like the Europa Clipper, which was proposed in the 2010s. The Clipper, designed to fly multiple close passes over Europa, would use a suite of instruments to study the Moon's surface, measure its magnetic field, and search for plumes of water vapor that might rise from the ocean. These plumes, if they existed, could offer a way to sample Europa's ocean without direct contact, much like how scientists study the atmospheres of other planets. However, the idea of shallow reservoirs was always speculative. The challenge was that Europa's environment is extreme. The Moon is bombarded by intense radiation from Jupiter, and its surface is covered in a thick layer of ice that could be tens of kilometers deep. Even if water could rise through cracks, would it remain liquid long enough to be studied? This question became more urgent in recent years, as new simulations suggested that the process might be far more complex than previously thought. In 2026, a team of researchers published findings that cast doubt on the feasibility of these shallow reservoirs. Their model showed that if water from Europa's ocean were to rise through cracks, it would quickly lose heat to the surrounding environment. The water would freeze almost instantly, forming ice crystals that could clog the fractures and prevent further flow. In some scenarios, the process might take just hours to complete, effectively cutting off any chance of sustained interaction between the ocean and the surface. These findings challenged the long-held assumption that Europa's surface could act as a gateway to its subsurface ocean. Instead, they suggested that the Moon's icy shell might be a formidable barrier, one that could prevent the ocean from reaching the surface in any meaningful way. This revelation forced scientists to reconsider the strategies for studying Europa. If the shallow reservoirs were not viable, then the search for life would have to focus on alternative methods. The idea of plumes, for example, remained a possibility, though their frequency and composition were still uncertain. Alternatively, future missions might need to develop technologies capable of drilling through Europa's ice to access the ocean directly. Such an approach would be incredibly challenging, given the Moon's extreme cold and the immense pressure of its ice shell. But the possibility of finding life in Europa's ocean remains one of the most compelling questions in planetary science. The journey to understand this icy moon has been shaped by decades of discovery, from the first glimpses of its surface by Voyager to the detailed measurements of Galileo, and now to the simulations that reveal the complexities of its environment. Each step has brought us closer to understanding Europa's potential to harbor life, but also highlighted the many obstacles that lie ahead. As we look to the future, the search for life on Europa continues to evolve, driven by the same curiosity that has guided scientists for generations. The Moon's hidden ocean may still hold the key to answering one of the most profound questions in science: are we alone in the universe? For decades, Europa has captured the imagination of scientists and space enthusiasts alike. Beneath its frozen crust lies a vast, hidden ocean, possibly twice the volume of all Earth's oceans combined, sustained by tidal heating from Jupiter's gravitational pull. This subsurface sea has long been considered one of the most promising places in the solar system to search for extraterrestrial life. The logic was simple: if liquid water exists, and if it's chemically rich enough to support metabolism, then life might thrive. But the question has always lingered: how do we study this ocean? The answer, for years, has been tantalizingly close. Scientists have speculated that water from Europa's depths might rise through cracks in the ice, forming shallow reservoirs that could be sampled by future missions. These reservoirs, if they existed, would act as a bridge between the alien ocean and the surface, offering a way to analyze its contents without drilling through kilometers of ice. Yet, recent simulations have cast doubt on this long-held assumption. New models suggest that the journey from ocean to surface might be blocked by a process as simple as freezing. If water from Europa's depths rises through fractures, it would rapidly lose heat, form ice crystals, and clog the cracks, sometimes within hours. This revelation has shaken the scientific community, forcing a re-evaluation of how we think about Europa's potential to harbor life. But what does this mean for the search? And what questions remain unanswered? Let's dive deeper into the mysteries of Europa, the challenges of studying its ocean, and the unresolved debates that continue to shape our understanding of this icy world. At the heart of the debate lies a fundamental question: can water from Europa's ocean reach the surface at all? For years, scientists have modeled the moon's geology, assuming that fractures in the ice, perhaps driven by tectonic activity or tidal forces, could act as conduits for water. These fractures, if they were wide enough and persistent enough, might allow liquid water to escape, creating isolated pockets of liquid that could be studied by landers or probes. But the new simulations challenge this premise. By analyzing the physics of heat transfer and fluid dynamics in Europa's environment, researchers have found that rising water would encounter a critical problem: the immense cold of space. Europa's surface temperature is around -160 degrees Celsius, and the ice layer is thick enough to insulate the ocean from the frigid vacuum. If water were to rise through a fracture, it would immediately begin to lose heat. The rate at which this happens depends on several factors, including the depth of the fracture, the salinity of the water, and the surrounding ice's thermal properties. But the simulations suggest that even a small amount of heat loss would trigger rapid freezing. As the water ascends, it would form ice crystals that could block the fracture, effectively sealing it off. In some scenarios, this process could occur within hours, rendering the fracture useless as a pathway. This raises a crucial question: if the fractures close too quickly, can any water from the ocean ever reach the surface? Or is the entire concept of shallow reservoirs based on an assumption that may not hold? The implications of these findings are profound. For years, the idea of shallow reservoirs has been a cornerstone of Europa's astrobiological potential. These reservoirs would not only provide a way to study the ocean's composition but also offer a potential habitat for life. If the water is warm enough and contains the right mix of nutrients, microorganisms might thrive in these isolated pockets. But if the fractures close too quickly, such reservoirs may never form. This challenges the assumption that Europa's ocean is accessible, even in a limited way. Instead, it suggests that the ocean might remain isolated, shielded from the surface by a thick layer of ice. This would make direct sampling of the ocean's contents significantly more difficult. However, it's important to note that the simulations are not definitive. They are models based on current understanding of Europa's environment, and they come with their own uncertainties. For example, the exact temperature gradients within the ice layer, the distribution of fractures, and the dynamic interactions between the ocean and the surface are still poorly understood. Some scientists argue that the models may oversimplify the complex interplay of factors at play. Could there be other mechanisms that allow water to reach the surface? Perhaps not through fractures, but through different geological processes entirely. One of the most intriguing questions is whether Europa's ocean is entirely isolated or if there are alternative pathways for water to interact with the surface. The simulations focus on fractures as the primary means of transport, but they don't rule out other possibilities. For instance, what if water isn't rising from the ocean but instead seeping upward from the ice itself? Some researchers have proposed that the ice might contain trapped brine pockets, which could release water onto the surface. Alternatively, cryovolcanism, eruptions of water or other volatiles, might provide a way for the ocean to interact with the surface. These ideas are still in the early stages of exploration, and they highlight the fact that our understanding of Europa's geology is incomplete. The Moon's surface is marked by chaotic terrain, ridges, suggesting a complex interplay between tectonic forces and the underlying ocean. If the fractures close too quickly, could other geological features compensate? Could the Moon's dynamic environment create new pathways over time? These are questions that remain open, and they underscore the need for more detailed studies of Europa's geology. Another unresolved issue is the composition of Europa's ocean. While scientists have long assumed that the ocean contains saltwater, similar to Earth's oceans, the exact salinity, temperature, and chemical composition remain unknown. These factors are critical for determining whether the ocean could support life. For example, if the ocean is highly saline, it might have different physical properties than Earth's oceans, potentially affecting the behavior of water and the types of life that could exist. Similarly, if the ocean is colder than previously thought, it might form different types of ice or have different chemical reactions. The new simulations add another layer of complexity. If rising water freezes rapidly, it might not only block fractures but also alter the chemical makeup of the surface. Ice crystals formed from ocean water could contain dissolved salts or other compounds, potentially leaving behind chemical signatures that could be detected by future missions. However, these signatures might be difficult to distinguish from other sources of surface ice. This raises the question, could the surface of Europa hold clues about its ocean, even if direct access is limited? The search for life on Europa is also tied to the broader question of how life might exist in extreme environments. Europa's ocean is a prime example of an environment that is both alien and potentially habitable. If life exists there, it would have to adapt to conditions vastly different from those on Earth. For instance, the ocean might be devoid of sunlight, relying instead on chemical energy from hydrothermal vents or other sources. This is similar to the ecosystems found in Earth's deep-sea hydrothermal vents, where life thrives in the absence of sunlight. However, the new findings complicate this analogy. If the ocean is isolated, could life there evolve in ways that are even more distinct from Earth's? Or would the presence of a subsurface ocean still provide the necessary conditions for life to emerge? These are speculative questions, but they highlight the importance of understanding Europa's environment in detail. The challenge is not just to find life, but to understand how it might exist in a world so different from our own. Despite the uncertainties, the search for life on Europa continues to drive innovation in space science. The recent simulations have not ended the quest, they have simply shifted the focus. Scientists are now rethinking how to design missions that can probe Europa's secrets without relying on the assumption that water will reach the surface. One approach is to develop instruments that can analyze the Moon's surface for chemical signatures that might indicate the presence of the ocean. For example, if the surface contains compounds that are more abundant in saltwater, this could be a sign of interaction between the ocean and the ice. Another idea is to look for evidence of cryovolcanism or other geological activity that might provide indirect clues about the ocean's composition. These methods would require advanced technology and a deep understanding of Europa's geology, but they offer a way to explore the Moon's mysteries without waiting for water to rise through fractures. The scientific community remains divided on the implications of the new findings. Some researchers argue that the simulations are a necessary correction to previous assumptions, while others believe that the models may not account for all the complexities of Europa's environment. The debate is not about whether life could exist on Europa, but about how to study it. The Moon's icy surface is a barrier, but it is not an impenetrable one. The search for life on Europa is a testament to human curiosity and the power of scientific inquiry. Even as new challenges emerge, the quest to understand this distant world continues. Whether through direct sampling, indirect analysis, or the discovery of new geological processes, the search for life on Europa is far from over. It is a journey that reminds us how much we still have to learn about the universe and how many questions remain unanswered. As we look to the future, one thing is clear: Europa's icy shell may hide more than just an ocean. It may hold the key to understanding the potential for life beyond Earth and the mysteries of our solar system. Europa's hidden ocean has made the icy Moon one of the solar system's most promising places to search for habitable conditions.
Scientists have hoped that water from this deep ocean might rise through cracks and form shallow reservoirs that future spacecraft could more easily study.
New simulations suggest that journey is unlikely because turbulent water would rapidly lose heat, form ice crystals, and clog the fractures, sometimes within hours. This part of our deep dive into the search for life on Jupiter's icy moon Europa just got more complicated. Focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Europa's icy crust has long captivated scientists as a prime candidate in the search for life beyond Earth. Beneath its frozen surface lies a vast, potentially habitable ocean, hidden beneath miles of ice. For years, researchers have speculated that water from this ocean might rise through cracks in the ice, forming shallow reservoirs that could be studied by future missions. These reservoirs, if they existed, would act as a bridge between Europa's subsurface world and the surface, offering a tantalizing opportunity to analyze its chemistry and possibly detect signs of life. But recent simulations have upended this hopeful vision, revealing a critical challenge that could make such a journey impossible. The new findings suggest that the journey of ocean water through these fractures is fraught with obstacles. Turbulent movement of the water would cause it to rapidly lose heat, triggering the formation of ice crystals. These crystals, in turn, could clog the fractures, effectively sealing them off before any material could reach the surface. In some cases, this process might occur within hours, turning the once promising pathways into frozen barriers. This revelation complicates the search for life on Europa in a profound way. It forces scientists to reconsider not just how water might reach the surface, but whether the surface itself could ever provide meaningful insights into the ocean below. If the fractures are too unstable to transport water, then the surface features we can observe, cracks, ridges, and possible plumes, might not be direct windows into Europa's hidden world. Instead, they could be transient, ephemeral phenomena, shaped by processes that are difficult to study from afar. This raises a broader question: how do we explore a world where the very mechanisms we rely on to gather data might be unreliable? The implications stretch beyond Europa. The search for life in the solar system hinges on understanding how water moves through icy environments, from Europa to Enceladus, Saturn's moon, and beyond. If these fractures are prone to freezing and clogging, it could mean that similar challenges exist on other icy moons, reshaping our strategies for exploration. For now, the focus shifts to alternative approaches. Scientists are now looking to design instruments that can peer through the ice without relying on surface reservoirs, such as advanced radar systems or drilling technologies that could penetrate the crust. Meanwhile, missions like NASA's Europa Clipper, set to explore the moon in the coming years, will need to adapt their objectives to account for these new findings. The search for life on Europa is no longer just about finding water, it's about understanding the dynamic, often unpredictable nature of icy worlds. As we refine our methods, the mystery of Europa endures, a reminder that the universe is full of surprises. For those who follow the quest for life beyond Earth, this chapter marks a turning point. The journey to uncover Europa's secrets is more complex than we imagined, but that complexity is precisely what makes it so compelling. If you've enjoyed this deep dive, consider subscribing to FactVerse for daily explorations of the cosmos. And if you have your own theories or questions about Europa's icy enigma, share them in the comments, we'd love to hear your thoughts. Until next time, keep looking up.